Welcome back, guys. In our previous video we solved this problem using the brute force method. Okay, this was terribly inefficient. This was our performance, which is not good, but today we're going to solve it in a more efficient way. Again, given a number n, find the number of trailing zeros in factorial of n. Okay, so a key to this algorithm, okay, is to notice that, say I was given the number 3, like in the previous example, 3, n equals 3. Okay, so we want to find f of n, which is just 3 factorial, okay, which is 3 times 2 times 1. The key to this is to ask yourself, in this expression, how many tens are in here? How many tens are in this expression? In this case, the number of tens in this expression is 0. There's 0 tens in this expression, so we return 0. Okay, let's take a different number. Let's say n equals 5. Okay, so f of n is going to be equal to 5 factorial, which equals 5, okay, equals 5 times 4 times 3 times 2 times 1. Okay, how many tens are in here? Okay, I know you guys might say there's no 10 in here, but actually there is, because there's a 5 right here and there's a 2 right here. So I can simply rewrite this expression as 10 times 4 times 3, which again, this equals 10 times 4 is 40, 40 times 3 is 120. So there's one 10 in here, the 5 and the 2, so technically we want to return 1. Okay, so let's give ourselves a second example. F of 10, say n equals 10, again is 10 factorial, which actually a third example, which is 10 times 9 times 8 times 7 times 6 times 5 times 4 all the way down. Okay, this is too long, but I'm just gonna say, so how many tens are in here? Okay, this is pretty straightforward. It's not pretty straightforward because it's a high number, but there's 1 10 here, so we have 1. Okay, how many other tens are here? There's 1 10 here because there's a 5 and there's a 2 somewhere here, so now we're at 2. Okay, but that's not all. Where else can we find a 5 and a 10, a 5 and a 2? Okay, so hold on, let me see that real quick. So technically, actually, there's only 2 tens in here actually. So there's only 2 tens in here because 5 can't divide in any of these other guys. So because 5 can't divide in any of these other guys, we're gonna have to return 2. So we return 2. Okay, for this. So do you see the trick in here? The real trick in here is, whenever we're given any n, it doesn't matter. All we really have to do is we have to find, in that n factorial, we have to find how many 5s are in there, because for every 5 there's going to be 2. Okay, because 5 is here, for every 5 you find there's going to be 2. So we actually can simplify. Rather than searching for how many 10s are in here, we can only search for how many 5s, because again, if you count from whatever, from n downwards, for every 5 you find, there is guaranteed to be a 2 in n factorial. So let's just put this to code and see what it looks like. So I'm gonna create a new function. Okay, actually I'm gonna create him below fact because I don't need fact, and I'm gonna call him trailing zeros 2. For now, I'll say pass. Again, I'll make sure I'm calling 2 and not 1 in here. Okay, as always, first we're going to define our count variable. Set it equal to 0. Okay, now while n is less than 0, okay, just kind of like we did up here, results, but in this case n. While n is less than 0, what do we want to do? We want to say n, we want to floor divide him by 5 because it's only 5 we care about, and then we want to return count. Okay, let's run it so we know there's 1, because again, we're looking for how many 5s are in there. Oh, I'm sorry, we have to update count. I forgot to update count. So once you floor dividing, you have to update count. Floors equals by n. Okay, now let's try this. Good, we get 1. So let's go ahead and copy this right here. keep track of the performance of our previous one, 5% faster, which is terrible. But now let's see how this new solution does. Okay, let's go ahead and indent everyone. Okay, I'm gonna go ahead and run this code first. Okay, accept it. Let's go ahead and submit. Bam. So from 5% speed, we went up to 90%. Okay, what a big jump. So as always, let's go ahead and step through this code and see what's actually going on. So I'm just gonna copy this guy right here. Okay, good. Let's go ahead and visualize it and see what's going on. Okay, then we declare a function where we define n equals 5. We call our function. Okay, so this is our global scope right here. This is our local scope of the function. Again, it's the same n variables, that's why n equals 5. Okay, then we initialize our count to 0. Now we're getting a while loop while n is greater than 0. Obviously 5, n is 5, 5 is greater than 0. Okay, then we do a floor divide and set it equal to n. So n floor divide 5. So 5 floor divide 5 is going to be 1. So n changes to 1 in the function scope, but it's still 5 outside of the function scope in the global scope. Okay, so now we're going to increment our count. Increment our count to 1. Okay, bam. And now we're going to try it again. We're going to floor divide by 5, which is 0. Okay, because 1 floor divide by 5 will give us 0. N is 0. We're not going to increment count, and then we're just going to return it. Bam, we return 1. Okay, let's try a second example where n equals 10. So we know 10 should have 2 in there. So I'm going to step through them real quick just to see. Okay, so count is already at 2. Bam, we return 2. So that's it for the video, guys. This is a more optimized way of doing this by just searching for how many 5s you can find in here, because for every 5 you'll find a 2, and 5 times 2 is 10, and anything multiplied by 10 is definitely gonna have a trillion zero. Take care, guys. I'll see you in the next one.